Let's move on to today's topic, strong induction. Yeah, this is the summary of previous topic, induction. We have these 5 steps. We can prove some claim using induction. But in this case, we have a specific starting point. So we want to generalize this for the different starting point. We have B here. So when you have different start point, uh, another natural number, how to solve it, how to prove it. The first, we need to define predicate uh, Q of K. And this is equal to P of K plus B for all K. So then, for all natural number n, Q of n is equivalent to, or for all natural number greater than or equal to B, P of n. So these two are equivalent. So now we can prove Q of 0, and that is equal to P of B, equivalent to P of B. Then we can see this relation again. Yeah, same. So we can rewrite this 5 step with a general starting point B. So yeah, the structure is same. We can use a different starting point B. So we can apply another example with different natural number, not 0. In this case, I want to show you an example that is starting from 3. This is 3 to the n is greater than or equal to n to the n square. So maybe if you have 1, this is 3, and this is 1. Yeah, that is correct. If you have 2, this will be 9, and this will be 4. That's still correct. But I want to show when the n is greater than 3. Yeah. So first, we need to define the claim. The P of n is 3 to the nth, and that is greater than or equal to n to the second n square. And for all natural number, that is greater than or equal to 3. Okay. So first, we need to find base case. Yeah, by the definition, we may need to use 0. Yeah, maybe if we use 0 here, and this is 1 and 0, and that's fine. But anyway, in this case, I want to start from 3 instead of 0, 1 for 1. But yeah, so base case will be 3. So we have 3 here. It is 27, and this is 3 square, and that is 9. So the base case is true. Next step, we want to show induction hypothesis. Suppose P of k is true for some arbitrary k that is greater than or equal to 3. Okay. Next step, we want to do this induction step to show P of k plus 1 is also true. So P of k plus 1, yeah, the left hand side, 3 to the k plus 1 is will be like this, and another hand, this will be k plus 1 square, right? If we simplify them together, this will be 3 multiplied 3k, and this is this, and this will be like this. But we want to make relation with the k. In k, the right hand side is k squared, and using this shape, we can multiply 3 to that part again, and still this is greater than that. Yeah, and this is will be k squared plus k squared and k squared. Yeah, 3k squared. And compared to this, same. Compared to this will be larger than that because the k is greater than 3. Yeah, equal to 3. So this is 6. Yeah, so if that is 3, but this is 9. It's greater. And this is 1. Yeah, definitely k squared is greater. Okay. So let's write down this again. This is p of k plus 1. We can write this like this, and that is greater than this one by the inductive hypothesis. Yeah, I said about this, and that is definitely greater than or equal to this part. And this is k plus 1 square. That means they are same. So p of k plus 1 also true. So we have shown the implication of this. If p of k is true, then p of k plus 1 is true. That means our claim is true by the induction. Okay. So there is another example here. In this case, we want to show this inequality with n is greater than or equal to 2. The first step, we have to define this claim over here, p of n, and we want to prove this by the induction. Base case will be this, and actually this is not 0, this is 2. Yeah, so base case is true, and we suppose p of k and p of n is true for some arbitrary number, n is greater than or equal to 2. We can write down this again here. This is smaller than this part, and we can apply this by the inductive hypothesis. Rearrange that will be like this, and then we will get this part, and by the factorization, this will be like this. So this shape is similar to this, the definition, and so we know the n plus 1 actually P of k plus 1 is true, and we've shown P of k implies P of k plus 1 is true. That means the claim is true. Okay, so what is the strong induction? Uh, the previous induction, we only see P of k implies P of k plus 1. But we know that the, the previous step, P of k minus 1, and to the starting point is true. So we want to make sure we can combine them together with AND. So all the previous steps are true. Then the P of k plus 1 is also true. That is a very strong induction. So yeah, this is the induction with different starting point, and this is a strong induction with same 5 steps. So we want to show the P of n, and we can uh, define the claim first, and so we want to show that using strong induction, the first step we need to prove the base case that is true. We need to find inductive hypothesis, but it is a little bit different from the previous one because we want to show all the previous step is true. So P of j is true for every integer j from b to k. That is all the steps from the starting to the current step k. So then we need to show p of k plus 1, that is next step. Then we can make them together. And so we know P of B, the starting point is true, P of K are true, the previous steps are all true, then we can make a conclusion. The P of N is true all the case uh, when N is greater than or equal to B. So now here is the previous example about the fundamental theorem of arithmetic. So there is a unique prime factorization for each composite. We use strong induction to prove that a factorization into prime exists, but not that it is unique. Okay, so this is that. So every integer greater than or equal to 2 is a product of primes. Yeah, it's true. Yeah. 2 is first prime, and next step will be composite prime. I don't know, but anyway, that is if that is prime or not, that is a product of primes. So right, P of n can be expressed as a product of primes for the natural number n is greater than or equal to 2. Yeah, we can use strong induction for this. Base case is 2. Yeah, that is prime. That's right. It is a product of prime, right? So induction hypothesis, we assume uh, the P of j is true for every integer j between 2 and k. Okay, so then we need to show P of k plus 1 is true. And that means k plus 1 is a product of prime. Okay, so we assume several k, actually 2 k's, prime or not. Thus, when the k plus 1 is a prime, then k plus 1 is the product of prime, simply. And it's not, it's composite, then k plus 1 is a combination of two number or more than that, a and b. We simplify this. There is be a and b. This is composite, and a is greater than 1, b is less than k plus 1, right? So by our inductive hypothesis, we know a is the product of prime, b is also a product of prime. So k plus 1 is equal to a multiply b, that is a product of p1 through the pr, and multiply prime q1 multiplies all the way to the qs. So all the component is prime. So this is a product of primes. That's why P of n is true for all natural number n is equal to n is greater than or equal to 2 by strong induction. Okay, strong induction is particularly useful when we need to analyze a method that on input k make a recursive call for an input different from k minus 1. And but yeah, there is an example, binary search for a problem of size k that is greater than 1. It makes a recursive call to a problem of size roughly k divided by 2. So we want to analyze this particular method by strong induction, but we could using recursion. So we will use strong induction to analyze other functions with recursive definition. That is recursion in other way. Okay. There is some recursive definitions of some functions. The first one, f of 0, that is 0, f of n plus 1, that is next step, and n plus 1 will be defined by recursive function, that is fn, the previous step result, plus 1. And this is just another number, like we can start from 0, and next step is 1 more, that is 1, another 1 more, 2, 3. So we can define natural number using that. And next step, g has different, so it starts from 1, and the g of n plus 1 is 2 cross g of n. That means the next result will be multiplication of 2 of previous step. So the first step will be 1, next step 2, 2 multiply 2 is 4, 8, like this. So it is multiplication of 2, and another one is factorial. So 0 factorial is 1. We can define n plus 1 factorial is n plus 1 cross n factorial. Then we can get the result. And next one is much more complex, which is function h. H is 0 will be 1. When you want to find next step, h of n plus 1, you need to apply 2 to the n of n. So the first step will be 1. And next step will be 2 to the 1, the first, 2 to the first, that will be 2. Yeah, we have 2 now. Next one, 2 to the second 2 square, that is 4. We have 4. Next step is 4 to the 2 to, not 4, 2 to the fourth. Yeah, that is 16. Yeah, this is kind of complex sequence, but we can define this kind of function using recursive definition. So again, we have seen this before, but now I'm going to use a recursive definition for the factorial. That's why I swapped the location of left and right. Now this one is n factorial is less than equal to n to the nth for all natural number n. So let p of n be n factorial is less than equal to n to the nth. We need to prove this. First step, the base case when n is equal to 1 and 1 factorial is 1, 1 to the first is 1. So p of 1 is true. Yeah, now let's assume p of k is true for some case k is greater than equal to 1. Yeah, then we need to show p of k plus 1, and that is k plus 1 factorial, k plus 1 to the k plus 1. So, uh, so now we want to use the recursive definition. The factorial multiply previous result and next step. So here k plus 1 is this is p of k plus 1, and this is equal to the previous step k factorial multiply k plus 1, and that is less than this, and this one also less than this because k is greater than equal to 0, and this is exactly same to the definition of this right hand side. So that means the p of k plus 1 is true by the definition of factorial. So therefore, the p of n is true for all the case n is greater than equal to 1 by induction. So another interesting function to generate this Fibonacci number by the recursive definition. So we have f0, that is 0, and f1 will be 1, and then we need to generate another number after that. This function has two recursive core here and there. So this is one step previous, and this two step previous. So if we combine them together, we will get the current. So yeah, this is interesting to show this kind of shade. The first one is 1, the second is 1, the next one is combine that together 2. Now this is summed by these two, it will be 3, 3 and 2 will be 5, 5 and 3 will be 8. And yeah, this is very interesting sequence. So it has very strange steps. Each step has same doesn't have same number and doesn't have simple uh, equation to calculate. It always use a recursive definition. Uh, we're going to cover this recursion later, and this is very useful in algorithm implementation, like binary search tree, binary search, and quick sort, merge sort, that kind of things. Okay, this is end of this class.